Welcome to another deep dive customized specifically for you, the learner. We know you are actively preparing for a major milestone right now, and today we have a very precise mission. We are going to master Linux permissions.
Right, and this deep dive is engineered to serve as your definitive audio study aid for that ethical hacking certification you're working toward.
Exactly. On the desk today, we have, it's a pretty rigorous stack of materials. We're looking at a set of field scenarios, a really dense technical content guide packed with permission facts, and a highly classified slide deck titled Linux Permissions Playbook.
It is a formidable stack of information, but honestly, it's absolutely foundational because in the realm of information security, understanding permissions isn't just about memorizing command syntax.
No, it's really the difference between an impenetrable fortress and a wide-open backdoor.
Yeah, exactly. When we analyze a system compromise, the root cause often traces back to just a single misconfigured permission string.
Okay, let's unpack this. Today's structure is going to be highly interactive. We are going to walk you through this playbook step by step, vocally transitioning slide by slide, so you can follow along directly with your visual materials.
And the goal here isn't just rote memorization.
Right. We want you to understand the why so you can analyze and evaluate these concepts like a true cybersecurity pro. Which means as we progress between slides, we will pose open-ended scenarios that require you to pause the video and formulate 2 to 3 sentence responses for your study notes.
That is definitely the best way to hit those higher tiers of Bloom's taxonomy.
All right, let's get into it. We're transitioning to slide 1, which is the Hacker's Playbook Mastering Linux Permissions.
This slide establishes the baseline tactical mindset required for this material. As you prepare for an ethical hacking role, your perspective just has to shift.
You're not looking at Linux as just an operating system anymore, right?
Exactly. You have to start viewing it as a complex series of locks and keys. You are looking at the foundational mechanics of how the kernel governs access to data structures.
Which brings us to the architecture of those structures. Let's move to slide 2, the core concept inodes and the VIP list.
So before we talk about permissions, we have to talk about where they actually live.
Yeah.
Every single file and directory in a Linux system is tethered to a digital ID card, basically.
The inode.
Right, the index node. The inode doesn't store the actual data of the file, and it doesn't even store the file's name. It stores the metadata.
Things like modification time and size.
Yeah, and critically for our purposes, the mode. The mode is the specific segment of the inode that dictates access permissions.
And the slide breaks this mode down into 3 distinct access categories: user, group, and other. Let's use the VIP club bouncer analogy from the slide to wrap our heads around this.
It's a great analogy. So the user owner is the VIP who actually rented the table at the club. They have ultimate control over their space.
Right, and then the group represents their entourage.
Exactly. They get past the velvet rope because they are with the VIP. They have elevated access that the rest of the club doesn't get.
Yeah.
And finally, other is just the general public.
Standard guests who can maybe be in the building but definitely can't access the VIP table.
Right. But there is an ultimate VIP bypass here, which the slide highlights. The root user.
Ah, yes, the owner of the club.
The root account ignores all bouncer rules entirely. It bypasses the inode mode checks completely.
Okay, so for your study notes here is your first open-ended prompt. Pause and explain in 2 to 3 sentences how the sequential evaluation of user, group, and other could theoretically be manipulated if an attacker compromises a low-level account that happens to share a group ID with a high-privilege service.
That's a great scenario to think through.
All right, let's transition to slide 3, the big 3. Read, write, execute.
These are the 3 basic permissions. Read is represented by the letter R and the numerical value of 4. Write is W with a value of 2. And execute is X with a value of 1.
Let's bring those numbers to life with our club analogy. So read, which is 4, is like just looking at the club from the outside. You can see what's going on, but you can't touch anything.
Yeah, and write, which is 2, is actually going inside and rearranging the furniture. You can alter the environment.
And execute the value of 1 means you are getting on stage and performing. You are actually running the show.
Exactly. And there's a major quiz trap here that we need to point out. Never just guess the numbers.
Always do the math.
Always do the math. If a user needs read and write, you add 4 and 2 to get 6. Don't try to memorize every combination. Just rely on the addition.
That mathematical certainty is super helpful. Let's advance to slide 4, files versus directories, the hidden difference. And here's where it gets really interesting. I mean, this honestly kind of shocked me.
You're talking about the execute permission.
Yes. The hidden difference there. Because for files, it just means running a program, but for directories, it means physically entering the directory.
Right, it dictates traversal. And this is a mandatory pairing explanation we need to dedicate some real time to because of a specific quiz example on the slide.
The prompt asks, what are the minimal permissions required to allow a user to list the contents of a directory?
And the answer is R-X. You absolutely must have both read and execute.
Let's detail explicitly why both are mandatory.
Let's go back to our restaurant or club analogy. Having read permissions, the R is like holding a physical list of all the tables inside a restaurant.
Okay, so you know what's in there?
You know the names of the tables? Yes. But without execute the X, you aren't allowed to walk through the front door.
Ah, so your packets are basically blocked at the firewall.
Exactly. You cannot traverse into the space to actually look at those tables. You must have both to list the contents properly. Without the traversal right, the read right is virtually useless for a directory listing.
Okay, time for your next open-ended question to process. In 2 to 3 sentences, articulate why granting read access to a directory without execute access might actually be used in a highly restrictive Dropbox scenario where a user can deposit files but not browse the existing contents. Let's translate this theory into syntax now. We are moving to slide 5, cracking the octal code.
Here we see the standard 10-character string you see when you run a directory listing. -R, WX, R, WXR, --. The goal is to translate this string into its octal code.
Let's do a step-by-step translation analogy. So first, we scan the very first character independently. A hyphen means it's a file, and a D means it's a directory.
Right, so we instantly know this is a file. Next, you chop the remaining 9 characters into blocks of 3.
User, group, and other. Let's walk through the math. Block 1 is RWX, that's 4 plus 2 plus 1, which equals 7. Block 2 is RWX. Wait, actually, looking at the source image here for the group, it shows RWX dash.
Good catch. So RW dash is 4 for read, plus 2 for write, and 0 for execute. That totals 6.
And the final block for other is R dash dash. That's just a 4 for read. So user is 7, group is 6, other is 4. The total octal code is 764.
That ability to visually parse the string and calculate the octal instantly is a mandatory reflex for you.
So how do we manipulate those numbers in the field? We are advancing to slide 6, tactical command chmod letter syntax.
The primary tool here is chnod, which stands for change mode. Using the letter syntax, you target the entity plus or minus the permission.
The slide provides a great tactable string chmod g plus w comma o minus r comma o minus x customer underscore list.
Right, so that is adding write access to the group while removing read and execute from others.
I want to point out a major quiz trap here. If a test asks you to remove all permissions for herd, others watch out for distractor options like O minus W.
Yeah, that is a classic trap. Because if write is already removed, subtracting write again doesn't magically remove read or execute. You have to explicitly target what is there.
But hackers and admins usually prefer octal write. Let's transition to slide 7, tactical command chmod octal syntax.
They prefer it because it's incredibly fast and absolute.
Let's review the mission on this slide. The user needs read, write, execute, so that's a 7. The group needs read, execute, which is a 5. And others get absolutely nothing, so 0.
Right.
So why do the distractor commands fail here, like chmod 771?
Well, 771 gives everyone execute power. The one at the end is a massive vulnerability.
And chmod 755.
That gives everyone read and execute power, still fails the mission. The only correct answer is chmod 750.
Which brings us to a core philosophy. We are shifting to slide 8, field scenario, the principle of least privilege.
This principle is the bedrock of system architecture. You give a user exactly what is needed to do their job and nothing more.
Let's look at the IT support ticket scenario from the quiz. A new manager gets access denied to a file. They aren't the owner and they aren't in the group, but they do need to read and write to this file.
So they fall into the other category.
Let's do the math for other. Read is 4 plus write is 2 equals 6. Now I want you to think critically here, learner. Why is applying chmod 777 a terrible idea here?
Because it grants global read-write and execute access. It's way too much access and a major security risk.
So 666 is the correct answer, so write down your response to this for your notes. In 2 to 3 sentences, describe a situation where applying chmod 777 to a temporary directory might actually be deemed necessary for a specific application, and explain the compensating security controls you would need to monitor it.
Excellent prompt.
Okay, let's explore special operations. We are excitedly transitioning to slide 9, special operations, the SUI bit.
This is where things get really fun. Sometimes a normal user needs to execute a file with root powers.
Let's use a vivid step-by-step analogy for this. Imagine a regular retail employee who needs to do one specific task on a cash register that requires a manager. The manager hands them a temporary manager override key just for that one task.
That is exactly how the SUID bit works. The set owner user ID. To activate it, a fourth octal number is appended to the absolute front of the string.
So how does a standard 0755 become 4755?
The 4 represents the SUID bit, which is binary 100. When activated, the file executes as if the root user were running it. Symbolically, the X in the user's block becomes an S.
This is a huge target for privilege escalation and ethical hacking. But what happens when the standard user group other buckets just aren't granular enough? We are advancing to slide 10 beyond basics, intro to ACLs.
Right. What if you want to invite exactly one specific person into the VIP club without letting their whole entourage in?
You can't just change the group permission.
No, that exposes everything. You need access control lists, or ACLs. They bypass the broad group rules for specific named entries.
Let's look at the tools to view these. We are moving to slide 11, interrogation tool getFackle.
The standard listing won't show you the details, just a plus sign indicating an ACL exists. You have to use getFackle. The flags you need are -A for the file ACL, -D for the default, and -R for recursive.
Critical exam intel point here. Learner do not confuse chmod, which changes the basic permissions, with getFackle, which merely displays the detailed ACL lists.
Interrogation versus modification.
Right. And for modification, we transition to slide 12, modification tool setFackle. We really need to dedicate some extra time to explain the power and use cases of some specific flags here.
Absolutely. Let's dive into -R, the recursive application flag. Imagine you just acquired a massive new company server with thousands of nested folders.
You definitely do not want to change those permissions one by one.
It would take forever. Instead, -R pushes the new ACL rules down the entire directory tree instantly. Every file and folder inside inherits the rule.
Super powerful, but also super dangerous if you typo the command.
Extremely dangerous, which is why you also need to understand the -K flag for removing default entries.
How does that work?
Well, default ACLs can act as a template, causing newly created files to automatically inherit unwanted permissions. If a folder has a bloated default template, -K is the surgical tool you use to wipe that default slate clean.
Awesome breakdown. Now there's a massive quiz trap from the sources on this slide. The command setfickle-mu:\Allenbury-Smith:\R.
Pay very close attention to that U:.
Yes, the U: means it grants the user Smith read access. It does not mean it grants access to the group that Leaguesmith belongs to. Precision is everything.
The command line takes things very literally.
Okay, let's test that precision. We are moving to slide 13, threat recognition, read the strings.
An ethical hacker needs to be able to translate English requirements into a 10-character string instantly.
Here is the scenario. Only the owner can modify. Only the group can read. Let's eliminate the wrong answers.
Well, we instantly throw out anything that gives the group write or execute.
Right, and we throw out anything that gives other any access at all.
Exactly. So working through the logic, the owner needs read and write, so that's RW-. The group only needs read, so R-. And other gets nothing, so --.
Bringing it all together, our string is -RWW-R-.
Spot on.
Here is your final open-ended prompt learner. In 2 to 3 sentences, summarize how understanding the translation between human requirements and 10-character strings assists an ethical hacker in quickly identifying misconfigurations during a vulnerability assessment. Okay, we are in the home stretch. Let's advance to slide 14, the final exam cheat sheet.
This is your recap of the 4 pillars. Math facts, knowing your 4, 2, and 1. Special operations like that mandatory read and execute pairing for directories, and the SUID bit.
Tactical commands, knowing your chmod versus your setFackle.
And finally, the least privilege rule, giving only what is absolutely necessary.
Which brings us to our final slide. Slide 15, mission ready.
You now have the blueprint. You know the traps, and you have the analytical framework to ace your certification or conquer your next IT challenge.
So what does this all mean? It means understanding Linux permissions isn't just about passing a multiple-choice quiz. It's really about mastering the underlying architecture that keeps global data secure.
And knowledge is really most valuable when it's applied. Be sure to use this deep dive alongside your video study aid to truly cement these concepts.
Before we go, I want to leave you with a final provocative thought. We talked about how the SUID bit the 4755 grants root execution powers to a normal user. But imagine a scenario where a hacker discovers a vulnerable, obscure text editing program on a server that has the SUID bit accidentally left on. Given that a text editor can read and write files, what kind of absolute chaos could they unleash, and how would you as the system administrator track it down?
That is exactly the kind of threat modeling that separates the novices from the professionals.
Thank you for joining us on this Deep Dive Learner. Review your slides, master the math, and keep asking the big questions.